Alright, hello everyone, and welcome to Lesson 6 of Unit 8 for the AP Chemistry curriculum. Today we are talking about molecular structure of acids and bases. Today we are explaining that acid-base behavior is based on reversible proton transfer and that the strength of acids and bases depends on molecular structure. Strong acids have very weak, highly stabilized conjugate bases due to factors like electronegativity, resonance, and inductive effects. Strong bases have very weak conjugate acids. Common weak acids that we're going to talk about today are carboxylic acids, and common weak bases are going to be nitrogenous bases like ammonia and carboxylate ions. Overall, the key idea is that the greater stabilization of the conjugate base increases acid strength, and this stabilization can be predicted by analyzing the structure of the molecule. Acid and base strength depends on how easily a substance donates or accepts protons, which is directly related to the stability of its conjugate partner. The more stable the conjugate base, the stronger the acid, and likewise, the more stable the conjugate acid, the weaker the base. And this leads to our key rule of this lesson: strong acids and bases always have weak conjugates, and weak acids and bases have relatively stronger conjugates. So we know bases want to accept protons, and when a base has a negative charge, you would think that it's going to have a high affinity for a proton. Now, the strength of that negative charge is going to tell us how weak or strong the base is. So let's start out with resonance. If we have resonance in a molecule, the negative charge is no longer going to be concentrated. It's going to be spread out between multiple atoms. So for example, if you look at these two molecules on the right, you will see that this pi bond here can bounce in between the two oxygens, which means the oxygen negative charge is not concentrated to one side. It's actually balanced out between both oxygens. That means that because of resonance, that negative charge is going to attract a proton less. The other factor that can influence strength of a base is electronegativity in the elements within the molecule. So looking at these two molecules on the right here, we see that they're the same except for the atoms connected to the carbon on the left. So we can see in the top molecule, acetate, we have hydrogens. On the bottom, we have fluorines. Now, remember, the strength of the base depends on how concentrated that charge is, right? Because the more concentrated the charge, the stronger the attraction to the proton. However, if we have extremely electronegative atoms like fluorine, that negative charge is going to be pulled in the direction of the fluorines, which means that negative charge is now spread out, which means it has a lower attraction for a hydrogen. So with that information, look at these two molecules on the right and tell me which one is a stronger base. And if you chose the top molecule, you would be correct. And that's because it has a more concentrated negative side of the molecule, because the hydrogens and the carbons are not very electronegative, so they're not pulling away from that electron density. All right, so which of the following would you expect to be the strongest acid? So before we answer that question, let's go ahead and draw out the Lewis structures of these acids. Now for me, when I'm trying to figure out what is the strongest acid, I'm going to look at the conjugate bases. So let's go ahead and draw out the conjugate bases. Now all three of these conjugate bases have a negatively charged oxygen. However, remember what we learned about electronegativity. the more electronegative other atoms in the molecule are, the more they're pulling away and spreading out that negative charge. So we know out of these three that chlorine is the most electronegative, which means for this molecule, the electron density is going to be more spread out rather than concentrated. And then comparatively, iodine out of these three halogens is going to be the lowest electronegativity, which means this oxygen is going to have the most concentrated negative charge, which means it's going to have a higher affinity for a proton. So if ClOH creates the weakest conjugate base of the three, then that means that is going to be our strongest acid out of our three options. When a carboxylic acid loses a proton, it forms a carboxylic ion. The negative charge in this ion is delocalized over two oxygen atoms through resonance, meaning the charge is spread out rather than concentrated on one atom. So because it has resonance, you would think, okay, this is more stable than it would be if it did not have resonance. However, these carboxylate ions are only partially stabilized, so they can still easily accept a proton. And because of that, carboxylic acids are still considered weak because their conjugate bases are still able to accept that proton and become a base. So what evidence explains why nitrogenous bases are notoriously weak? So if we're looking at NH3, when it acts as a base, it's going to accept a proton and become NH4+, which is ammonium. Now, one of the characteristics we've been talking about is electronegativity. Now, nitrogen is moderately electronegative, which means the pull that it has for a proton is not super strong. So even though it has a lone pair to donate to a proton to form a bond, nitrogen isn't attracting protons as readily as something like fluorine or chlorine. The other evidence we have is that when something like ammonia accepts a hydrogen and becomes NH4+, it's now a positively charged species, which is not highly stabilized. And because of that, it readily wants to lose that H+ ion or donate a proton and regain that stability. So what you need to know about nitrogenous bases is that they are weak because they only partially accept protons in solution, because their lone pair is available but not reactive enough to drive a complete ionization. Which base is stronger? Explain. So both of these have a nitrogen with a lone pair, which means it can donate this lone pair to a proton and become a positively charged ion. Now the question is, which one is stronger? Well, we know that when we want a stronger base, we want a more localized or concentrated negative charge. And on the right molecule, we have fluorine atoms, which are highly electronegative, and are going to be pulling that negativity away from nitrogen. So in that case, ammonia or NH3 would be the stronger base. All right, let's do an example. The table above includes the Lewis diagrams of the conjugate acids of some weak nitrogenous bases. Based on the relative stability of the conjugate acids, Which of the following bases has the largest value for Kb? So first let's figure out what it's asking. It wants to know the base that is the strongest, because remember, a large K value means that we have a product-heavy equilibrium, which means it's strong. So we're looking for the strongest base. And remember, the stronger base is going to have a weaker or more stable conjugate acid. So looking at these conjugate acids, we can see the key difference is what is attached to the nitrogen. So we have carbon, another nitrogen, oxygen, and chlorine. And we can see those have very different electronegativity values, with chlorine being the most electronegative and carbon being the least electronegative. So remember, an acid is determined by its ability to donate a proton. So if we have a stronger pull of electrons from this chlorine, that means it's going to be much easier for this nitrogen to give up one of the hydrogens. So this one is going to be the strongest conjugate acid. And because carbon is the least electronegative, that means this one is going to be the weakest conjugate acid. And because we are looking for the weakest conjugate acid, because that points us to the strongest base, that means A would be the answer for this question. All right, so in this lesson, we learned that acid and base strength relates to the stability of the conjugates. Strong acids like hydrochloric acid, hydrobromic acid, and nitric acid fully dissociate because their conjugate bases are very stable, while strong bases like group 1 and group 2 hydroxides have very weak conjugate acids. Weak acids such as carboxylic acids only partially dissociate because their conjugate bases are only moderately stabilized, and they're moderately stabilized because of resonance. So equilibrium does not go to completion. Weak bases form relatively stronger conjugate acids, and so overall the key idea is that greater stability of the conjugate base or acid leads to weaker reactivity, and this balance determines whether a substance is strong or weak. So a quick overview. Structure determines stability. So whenever you're looking at the stability of an acid or a base, look at its structure and determine how that stability affects its strength. So the more stable it is, the weaker it is. The more reactive it is, the stronger it is. And then when you're looking at a strong acid or a strong base, you should know that their conjugate will be much weaker and more stable. And then when we have a weak acid or a weak base, just know that their conjugate is going to be stronger than that original acid or base. It's not going to be a strong base or a strong acid necessarily. It's just going to be stronger than its pair.